Good evening, and welcome back to Robot in 3 Days, brought to you by Full Moon Robotics. We have a lot of exciting content for you this evening. So, Emma, what can the viewers expect to see?
Right now, we will be talking to Kevin to hear about the cat of the robot.
I hear he's been working on that non-stop today, literally from this morning. So, let's hear from him now. Hello, Kevin. How are you doing?
Hey, I'm doing pretty good.
Awesome. So, I hear you've been doing a lot of CAD work today.
Yep, and I'd be more than happy to show you all around. So from this morning, we started off with a empty sketch, and we basically got the entire drivetrain CAD'd from scratch. So everything in the model for the drivetrain should be mostly accurate to how it is on the robot. Obviously, there's no electronics board model, but we're going to forego that for the time being, just for the sake of time. But otherwise, it's a very detailed model and is accurate to what we have on the robot. We also got the intake mostly modeled, and as you can see, we can actuate it as it would in real life. Only part missing from there is the roller for the intake. And the reason I haven't put that on there yet is because I've been spending the past couple of hours working with the in-person team at the RoboDogs workspace to come up with the design for the shooter and the hopper that's going to feed it. So what you see here is this big cylindrical block here and what semicircle, and that's just kind of a stand-in to show the space that our shooter is going to take up. We only have that in there so we can work out the geometry. So this is our rough prototyping basically that we can do virtually because of CAD. So as you can see here, this little ramp, that's what we're calling the ravine, which Tejas so greatly named. And what this is for is once we intake the power cells, they're going to hop up into this, and the ravine is going to help you use gravity to help the power cells kind of sequence themselves and be fed into the shooter in an orderly manner that we can control. So we've been working on figuring out what the best shape for this ravine is and how to get it to feed into the shooter. So what you see right now is our first prototype where we just had 3 rectangular pieces kind of lined up with each other. And we identified some places where this might fail. For one particular important thing to note is we are sacrificing the width up here by using rectangles. So that's going to make it harder to hold more power cells. So what we've been doing within the past half an hour is we've started on this new design that has a wider width towards the intake side and kind of funnels it down more towards the shooter. And so I've been working on some nice 3D geometries here. So I've been doing a lot of math on my whiteboard over here to figure out how to get it to fit. But hopefully we should have that modeled and we can give the people at the RoboDogs workspace a better idea of what to build for our hopper and ravine system. And I guess with that, I can hand it over to the RoboDogs workspace.
That's excellent.
Awesome.
Love to hear it.
Yeah, so I can definitely chime in on that. I can definitely chime in on that too. We're out here kind of in the workshop building everything that pretty much Kevin has said so far, and I want to talk about a design process really quick, kind of like how we came to these designs, what was the thought process. So we originally started out with just a simple conveyor belt mechanism that just scored and lower goal. And pretty much once we started looking at what this season entailed, we realized that shooting higher goal would allow us to get more points. And we not only want to shoot higher goal, we want to shoot higher goal from like different areas on the field. So immediately our first thought was, how can we redesign without having to change as many things, like too many things on the robot? You know, we kind of want most stuff to stay similar. So that's one way that kind of 2020 is a completely different year, 2021, sorry, because in the past years, you know, you kind of build a robot from scratch, but this year we've kind of had to take what we already have and build something that can be applied to that, but without changing too much. So you're a lot more limited too in the creative area. So that's when we realized that, you know, we can add kind of a hooded shooter on the back, which is what Kevin showed earlier, the little semicircle. And we can also add that hopper, which we call a ravine, because it looks pretty much like a ravine. So we're going with that one. And yeah, there's been a lot of work going into the hooded shooter. I'm hoping maybe I could steal one of the Jake just handed me one of the side pieces. So here's what we currently have right here. This is one of the side pieces that we made. It pretty much has a hole in the middle here where my pinky is for a bearing, and we've manufactured all these little holes inside. So this really gives us a lot of prototyping freedom, because now we can test different compressions on the ball based on where we want to put certain shafts. So how this works is, let's see if you can see the inside. Here's a shaft with our flywheels on the inside. So yeah, it pretty much draws it in here, spins through, and there's shafts that'll be just through a certain amount of these holes to go through. So the shafts could be on the inside here, or they could be at the very top. So pretty much.
I've got a question for you, real quick.
Yeah.
So, how did you make all those holes? Did you drill those manually, or did you have some sort of way to automate that process? Because that's a lot of holes to drill right there.
That's exactly what I was thinking.
Yeah, we marked them up, and then we made sure to hole punch all of them, and then drill them manually. It didn't take as long as it seems, but it was definitely a lot of effort. I will say that.
Well,
Wow.
I think it's definitely an effort well spent.
Those custom pieces were just originally square aluminum sheets, so we've had to get the corners rounded and everything.
So
That's
pretty much
really
everything you see
impressive,
here, we've just machined out ourselves today. But,
Incredible.
That's
And
awesome.
then we also have the wooden dowels for the supports, adjustable supports.
Sorry, what was that for? I missed it there.
Yeah, so pretty much these wooden dowels when attached, yeah, so they'll attach to the little holes that we have here, and that's why we have certain holes. We can control, like, if we want each dowel to be farther in. Yeah, yeah. We can pretty much control if we want each dowel to be further in like this or further out on each hole. And so we'll have a total of 11 dowels kind of going around all these holes like this. And then pretty much they just attach to the second hood, which is exactly like this, which we're still working on a little bit. It just needs the holes in it. But yeah. So 2 hoods connected like this, and that'll be a full shooter there.
And then it's a plexiglass back end for the ball to smoothly roll out.
So those wooden dowels are going to serve as the spine for us to shape the plexi with. And those extra holes give us adjustability. So when we're tuning, we can make sure we get the right amount of compression throughout the whole hood.
That makes a lot of sense.
This is incredible, especially considering how much of this was done solely today. You guys have made amazing progress, and I'm really excited to see what you guys can continue to do tomorrow.
Yeah,
All right.
thank you.
Thank you so much, guys. Let's head on over to the e-garage space, and we can hear how they're doing over there.
Hi, thank you for coming and joining us with the e-garage. I'm Alex, representing the build team here. I'll be talking a bit about some of the build updates that we have today. So as you see, we've moved our robot off of this build space, and we have it out here. So you'll notice one of our mechanisms that we took off is actually back on. That's our main intake here. And if you remember, we used to have this spur, which is now in the front, running along the back. And the reason we've moved this up here is so now when the arm comes up, you have this open space in the robot, which wasn't available to us before. As a result, we can now put a hopper mechanism in here, and that will help us keep track of the balls and move the balls from our intake to the shooter. And it also helps give us a point that if we need to attach something later to redirect the balls, we can do that. Or we still have this available to redirect the balls. Made a couple modifications, taken a couple additional things off, and we've made this space as good as we can to help bring in area for our shooter. And then we will work on transitioning from the intake to the shooter mechanism. And now we've been doing a bit of dry practice and testing, so that has been going successfully, and we are good to show a little bit more about that.
All right, let's see it.
Yeah, so we've been working pretty hard on programming stuff for the past hour or so. We've done a lot of tuning and other miscellaneous debugging tasks. There's been quite a few issues in the code that we didn't really anticipate until now, and all of that has been worked out, and we're pretty much now able to drive. And right now we are just working on testing some autos for the first time, but that's something that we'll probably have to save until tomorrow to show off, just because we still have to work out some kinks with that. But teleop driving works properly. It's all characterized, running PID, and it's pretty smooth.
That's great. That's great. So what kind of issues did you run into while trying to get teleop working?
Well, we had some bugs in some input libraries that were basically making the robot move backwards in turn, like permanently. And I originally thought it had something to do with the characterization I just did, but it was in fact something to do with getting the inputs from the controllers that was the issue. But it's all been resolved and it works beautifully now.
That's great to hear. I like it. So how are you able to, how did you utilize PID in teleop?
Yeah, so basically this is sort of setting the groundwork for auto, but it applies to teleop as well, where instead of using just raw percentages to drive, it's now being controlled based on velocities. So the PID and characterization are sort of being fused into a single output measurement of voltage that's being sent to the motors, so that if it's moving slower than it expects to be moving, or if it's moving faster than it expects to be moving, it's able to sort of correct for that and stay at a consistent speed, where you wouldn't get that with a percent. For example, if like something is in the way of the robot, if you're just driving with raw percent, it might just slow down or stop. But if you're driving with PID, it knows, oh, I'm going slower than I'm supposed to be. So it'll start adding more power to be able to compensate.
That makes sense. That's really interesting. I believe I saw you posted some graphs earlier in our team Discord. Do you mind sharing your screen possibly and talking us through some of those?
Yeah, I can probably get some of those up, I think. Let me check. May take a minute.
All right, well, no worries. Take your time.
While he's getting those up, I think it's important to note that, especially for programming a robot, it can look like it's 100% correct on your screen, but until you actually get a chance to test it on the robot, you don't know what could be wrong with it.
Exactly.
Yeah, that's absolutely true.
So while we wait on that, Anupam, do you mind talking us through what you've done today, real quick?
Yeah, absolutely. I would love to. I think Trevor got his graphs up, so maybe he can go ahead.
Go ahead, Anupam, and then we'll come back to Trevor.
Sure. I would love to give an update on some of the things that the programming team has been working on as per content. So for the past couple of hours, Bennett and I, who are both on the programming sub team, have been working on a Git tutorial. So we're going to be releasing a video, hopefully by tomorrow morning, where we teach you how to create a project from scratch and link it with your GitHub account. So going through all those steps, and we're going to be teaching you some basic commands, how to stage files, how to commit files, and of course, an overview of what Git is and the advantages over using it over something like Google Drive or another way that you might be sharing files at the moment. And I think it's really important now than ever to be using a tool like Git, especially because now, with things being virtual, you're going to want a way to store your project in a central location, and Git allows you to do exactly that. So yeah, over the past couple hours, we've been working on preparing a script, narrating a few segments, and then making a few clips of explaining how Git works. So hopefully by tomorrow morning, we should have something ready and you guys will be able to look at it. So stay tuned for that.
Awesome. Thank you so much. I know GitHub was always something my team didn't know about until recently, so that's going to be really valuable to a lot of teams out there. So thank you again.
Yeah, and especially the younger teams who can get started on this early in their development and stick with it.
And it's something that's like not just applicable to FRC, but like if you go into a career in software development, Git and source control in general is something that you absolutely have to know. So you may as well get started on it now.
Well, awesome.
And what you can see on the screen right now is the graphs that they were talking about before. These were generated by our characterization routine. And it basically determines the relationship between velocity and voltage. So you can see what it's doing is it's doing a linear regression. And it's basically saying, for example, if I want to go at, say, 2 meters per second, it's basically able to look at this graph and figure out how much voltage it should be applying to the motor. And that basically helps the closed loop control system on the robot maintain velocity, because the PID is only really intended to correct for like deviation, where if it's not doing what it's supposed to be doing, this is basically telling it what it's supposed to be doing, where it's able to know if the controller is saying move at 2 meters per second, it says, okay, I should apply, say, like, I don't know, like 10 volts to the drive motors. And then if it's not moving at 2 meters per second, even if it's applying 10 volts, then the PID will start to take over and correct up or down depending on where the issue is.
All right, that all makes sense to me. But how did you go about creating this?
This is a utility that's released by WPILib. It's called FRC characterization, and it can do all sorts of things, not just drivetrains. For example, elevators, arms, etc. I have quite a lot of experience with this tool, and it's definitely a little bit complicated to get working. But once you do, it will change your life, because it basically, for more complex mechanisms like arms that rotate and have to deal with like compensating for gravity at different angles where the force of gravity may vary, this tool can basically account for all of that and make it move like ridiculously smooth.
So where did you learn to use this tool? Because this seems like something that teams all across the world should be using if it's so helpful.
Yeah, there's a lot of documentation for it on the WPILib docs. There's a section on robot characterization that walks over this a little bit. And then also just a lot of it I've learned from my own experience working with it. I used it last year, and I used it quite a bit. There were, I think, 3 or 4 mechanisms on my team's robot last year that had to be characterized with this tool. So I had quite a bit of time to work with it.
Very cool, very cool. Can you walk us through the graph on the bottom, please?
Yeah, so this graph is basically the same as the one up top. It's just instead of velocity, it's graphing acceleration. And while we're not really using this for like controller input, even though we theoretically could, it's still somewhat useful for autonomous to be able to say the path is saying that we need to be accelerating at this speed. So it's also looking over here and figuring out if it needs to add or subtract voltage from the base velocity that it's going at immediately to be able to get a more accurate estimate of what the voltage should be.
Nice, nice. I am blown away, honestly. So, all right, you've got all this and everything. What's your next step moving forward into the rest of the evening and tomorrow morning?
Probably tomorrow morning, we could start working on autonomous, because now that we have all of this and we can drive with closed loop and get accurate velocities, we could start making paths and working on the, I don't remember the exact name of it, but there's one of the infinite recharge at home challenges that involves following paths during autonomous. And this would basically allow us to do that. And we also installed a gyroscope today, which means that we are able to follow paths very accurately by estimating where we are on the field at any given time and comparing that to where the path dictates that we should be. And so it's able to sort of correct back onto the path that it's trying to follow if it gets knocked off or slides off. And it's just a matter of programming in the paths that need to be followed, and the code does the rest.
Nice. So in the case that you don't have a gyro, what happens?
We wouldn't be able to use the RAM. There's multiple pronunciations, but there's a follower algorithm that's included in WPI Lib called Ramsetti, I think. I don't know. There's a lot of ways of pronouncing it, but it basically uses that gyroscope input and does what's called odometry, which basically estimates the position of the robot on the field based on how fast each side of the drivetrain is moving and the angle that the robot's pointing at. And without a gyroscope, you wouldn't be able to get that angle. So you wouldn't be able to use that follower algorithm that's able to correct for getting off the path, but you could theoretically still follow paths. It just wouldn't be accurate. For example, if you got bumped, you wouldn't be able to navigate back onto the path automatically.
Nice. Well, does anybody else have any questions for Trevor and the rest of the programming team?
Can we see the robot drive?
Yeah, it should be good to drive.
Yes, we can. Can you guys hear me?
Yes.
Hey, it's Sam here, who's programming Speed on the Ground. What's up? I just want to say real quick that none of this would have been possible without our fantastic friends here, Mr. and Mrs. Off-Brand Power Cell. They're the real heroes here in all the work that we've been doing. Of course, they can't code like Trevor can. Anyway, I'm just going to take it through some quick paces. Trevor's the real wizard. He wrote all the code and figured out all the issues. This thing drives like a champ. Stand by for enable. I think we lost the RSL, but how's that for a robot?
Looking awesome.
That was wonderful.
Oh, it also does the spinny thing, the control panel. If you guys would like to see that, let me see if I can get you up close. Can you see that? Wait.
Yeah, we can see
Yes.
We're still working out some pneumatic issues that should be moving up and down as well, but right now it's not. We're still working out some problems with the PCM, I think.
Well, I'm sure you'll get it all sorted out. You've done an excellent job so far.
And we met our goal. The robot drives by the end of the day again. So good work, everyone. And thank you so much to the programming team and the build team and the feet on the ground to make this happen.
Yes, nice job, everybody. And thank you most to our viewers at home watching this. We really appreciate each and every one of you. And be sure to join us at 9 a.m. tomorrow morning, where we will continue streaming and give you an update on our progress throughout the day. Also, thank you to our sponsors, Relay, the NC State eGarage and Entrepreneurship, as well as the RoboDogs at Team 435, located in Wake Forest. We appreciate you all, and without this, this wouldn't be possible. So be sure to join us at 9 a.m. in the morning, and we'll see you then.